You can call me JC. Jean-Christophe and Robin is a bit like long. Okay, let's get started. Today we're gonna talk about packaging binary extension for Python. But first, let me describe who am I. I work at Kitware in our North Carolina office. I'm also the lead developer of 3D Slicer, a medical imaging and medical visualization platform. I'm the maintainer of Scikit-build, CMake and Ninja Python packages. I'm also the maintainer of the Python CMake build system. It's an alternative build system to streamline the building of CPython. And I also am the maintainer of Docross. Okay, what is the goal of this talk? Today we're going to identify the requirements for building CPython binary extension. We're going to outline the limitation of the current approach, and we're going to introduce our solution. The talk is going to be organized in few sections. First, we're going to review the packaging lifecycle. Then we're going to talk about binary extension. What are the problems? What do the impact? The state of the current tool. The requirements for a solution, our solution, the feature, and then what's next. Okay, if you haven't done so, you should go check the packaging user guide. It's a must-read. It contains a lot of useful references. This is a pretty complex diagram, and through the course of the presentation, I'm going to bring back that slide. I'm going to highlight some boxes, and I'm going to clarify some of the terminology. Okay, first, what is a source distribution? The synonym is also SDIS, or source release. It contains some metadata, source file, and it's needed for installing by tool like pip, and also for generating a build distribution. But where does that fit in the big picture? If you look back at our packaging lifecycle, at the top we have the development tree where we manage the revision of our source code. And then from that we can generate a source release, source distribution. Usually using setup.py as dist. Then we have the build distribution. What is that? It's also called bdist or will. It provides some metadata, also with some pre-built files. And the only things we need to do is to extract the content of a distribution into the target system. There's no build process involved once we get the build distribution. Where does that fit in the big picture? Development tree, we work on it. Then we have the source release, and from that we create the build distribution. Now let's talk about ABI, Application Binary Interface. This is an interface between two binary program modules, and making sure like module have a compliant ABI is usually the work of the compiler and also the package maintainer. And why is that important? A Python distribution could be either pure or non-pure. And pure distribution, it means it only includes a .py file basically. And it's not specific to any CPU architecture. There's no ABI for the pure distribution. And then what we call non-pure, it's what include basically compile extension, Cython module, compile Fortran code, and so on, and it's platform specific. And then what is a binary distribution? You have the build distribution that can be pure or non-pure, and the binary distribution is a build distribution that is non-pure, and it's platform specific and contain compile extension. And then we have the will. What is the will? The will is a format that describes how do you lay out the different files in your build or binary distribution. It's basically a zip file with the .whl extension, and it's described by PEP427. And in my presentation, there's a lot of links, and at the end, I will have a short URL so that you can get back to it and click on the different link and explore. Few examples of will, they usually are named like that. For the one who are non-pure, you have the name of the target system, many Linux, Mac OS X. And for the pure will, some of them are specific to Python 2, some of them are specific to Python 3. Some other one can work on both without any specific CPU or platform requirements. Okay, but where does the will fit in the big picture? We have the package lifecycle, And on the top right, we can generate the wheel, usually with pip wheel command, and then we get our wheel. They can be binary or not, meaning pure or non-pure. And then on the bottom left, we can also see Canopy, Debian, Conda, and Fedora. And to generate the package, you will install with the usual package manager, Conda or like apt-get or whatever package manager is used in your distribution. We also, part of that process is also to generate wheel and then repackage and so that we can distribute them and make them available to the user. What is the caveat of all of that? We have the packaging user guide. We have a section packaging a binary extension, but this section needs some tender love and care. It's labeled as incomplete, last reviewed in 2013. But fear not, a few days ago, we submitted few pull requests to help improve, and they got accepted thanks to THEA codes for reviewing and integrating so promptly. And other good news, yesterday we gave the tutorial about packaging. It was well received, and here you have the URL, and you can go look at it again. Okay, now let's talk about binary extension. Do they really matter for science? Yes, trust me. Now, let's look at the details. They speed up computationally intensive code. They allow to create wrapper module. They allow to access lower level feature of OS hardware, work with CPython. They allow to leverage multi-core, many-core, GPU, and so on. What else? They allow to leverage existing scientific code. We don't want to reinvent the wheel. We want to be able to compile Rust code, or Fortran code, or Cython code, and then access that from Python. It allows also careful and precise memory management, and it also avoids the parallel computing issue related to the global interpreter lock. Okay, but do you have some example of wheel? Yes, just to name a few: SciPy, Scikit-learn, SimEngine, MyAvi, Matplotlib, PyZMQ. All these packages include compiled binary extension and are then qualified as non-pure. What are the problems? Specifying the correct compiler and link flag is error-prone. Finding build-time dependency is difficult. Leveraging build tool like Make or Ninja is not possible. Building multiple extensions in parallel is not an option. Using your preferred IDE like Visual Studio, Qt Creator, you name it, to develop C or C++ code is not easily possible. Setting up a project with compiled module is tedious. Cross-platform development and distribution of extension module is a complex topic. Cross-compiling is horrendous. Who does it impact? Every one of you. You're writing the code, you're maintaining the project, you're installing the package. But fear not, now there is Scikit-build, a reliable and easy way to package your compiled Python project. State of the current tool. They handle the common needs, but they leave a lot to be desired, and they are not specialized for compiling. What are the requirements for such a tool? Reliably build native code, first-class support for system introspection, creating extension module for Python script, dynamically and statically linking extension module for use in embedded application, compiling, packaging, and publishing, all integrating with the Python ecosystem. First-class cross-platform support, and also cross-compilation capabilities. There's a clear need for a cross-platform building and packaging solution that support projects using compiled module and their user. Our solution, Scikit-build, is basically a bridge between CMake, your C++ project, your C++, Fortran, C, and Cython project, and also the Python ecosystem involving pip and setuptools. But what is CMake? We're going to cover that on the next slide. First, let's go back to the big picture with the packaging lifecycle and see where Scikit-build fit in the process. It allows to integrate with the existing tools. When you, for example, do pip install -e, to create your, to develop your extension. Or when you do when you generate the wheel with pip wheel, Scikit-build integrates with the existing tool, setuptools for that matter. And it also brings CMake, which is specialized in generating build system and compiling code. And it also integrates with the generation of specialized package like Conda, Fedora, Debian, and Canopy. Because to generate this package, you also have to build code. What are the benefits of using CMake? It's an open source, well-maintained and supported tool. Cross-platform build with first-class support for cross-compilation, system introspection capabilities, support for native build system. Means you can generate build system for Visual Studio, for Xcode, for Ninja, for Makefile. And there's also Python extension module support. And it doesn't depend on anything. It's available on supercomputer. You can compile it on supercomputer, and it's also available. The binaries are available in SciPy by pip install, in Conda. You can download the binary on any for any operating system. Okay, let's look at the trend of build tool. We have CMake, AutoTools, Automake, Bazel, Sconce, and the blue line basically is, according to Google, the popularity of CMake across the past like 15 years. And we clearly see the trend. CMake is gaining more and more momentum, and it's used in a lot of projects. What is Scikit-build? Scikit-build is not reinventing the wheel. It's not a new paradigm. It integrates with existing tools. It's not using setuptools extension or distutils.extension, but it can be used along. It's not a replacement for Canopy, Conda, or SciPy. It doesn't manage package. It only makes building them easier. It's not magic. You're still compiling extension module, but only with much less guesswork. Scikit-build is a drop-in replacement. Basically, you remove the from setuptools import setup, and you do from skbuild import setup. And then you only need to write a CMake list that describes what you build and how you build it. For example, layout of a Hello World project with a C++-based extension. We have the CMake list, we have the hello.cxx, the init.py, the setup.py, and the pyproject.toml. Let's look at the content of the setup.py. From skbuild import setup, we describe our package, hello, that's it. And then we write the CMake list that's going to be automatically be picked up by the system. And here we describe the name of the project, we include the Py extension module, we add the library, we associate other property to the library, and we install it. And that allows us to describe the build system. And then we also have the pyproject.toml, because since we need Scikit-build during the generation process, we need to install it before we even call setup function. But with the pyproject.toml, all of that happens under the hood. And you can also specify, if you don't want to use the tool on your system, CMake and Ninja, there's Python will have a label, and you're going to all the requirements going to be installed for you, and transparently. And then how do you build it? Pip wheel, dot, and then where do you want to generate the wheel? That's it. What are the features? Support for Python 2.7, 3.4 and above. Compiling environment. By default, we look up the compiler matching the Python version. You don't have to guess, okay, you need to use C++ compiler for Visual Studio 2008 for Python 2.7, Visual Studio 2015 for Python 3.5. It's going to expect that by default, but you can easily override that. It provides recommendation if the compiler is not installed. If you run the command and you don't have Xcode, you don't have Visual Studio installed, it's going to show you a meaningful error message where to download and how to install it. It also understands the common environment variable CC, CXS, CFlag. It means you can just set that and then build your wheel and going to inherit from this flag. It also supports a Ninja build tool on Linux, Mac OS X, and Windows like Ninja. Ninja allows to very efficiently build your code. When you have only one extension, it doesn't matter, but when you have a more complex project like TensorFlow, that will matter a lot. And you don't need to toy around with VC, vars, all.bat. You can just call it from your terminal on Windows, and it's gonna set the environment by leveraging existing code that was doing that. It also supports the developer mode. If you do pip install -e or setup.py develop, it's gonna copy the library in your source tree, and then you can easily develop your Python file. You don't have to always generate a wheel to use it. There is CMake and Ninja Python package you can install, as I mentioned earlier. By default, if you don't have a manifest.in, it's going to automatically package all the source using Git within your source distribution. It also supports fast incremental rebuild by skipping reconfiguration if relevant. It supports the usual keyword in your setup function, package dir, include package, etc., etc. And it also extends that with additional setup keyword. You can specify CMake argument you want to use. You can specify another relative install directory. You can specify where the CMake list is located. You can ask always to run CMake when you create your source distribution. You can change the amount of language that are associated with your build system. C, CXX, but if you want Fortran, you can specify that. It has a nice command line interface. You can pass option to CMake, but also pass option to the build tool. For example, here we do Python setup.py, bdistutils, -- the CMake option, and then another -- the build tool option. And the build tool option will be, for example, the option you will give to MS Build if you build with Visual Studio, or you give to Ninja or to Make. And Scikit-build also provides some specialized module, Python extension, to easily find out which flag you need to use to build your module. There's also a Cython module to bridge with the Cython ecosystem and generate the code, a NumPy module to easily find the header you need to create your extension, and also a F2Py module to more easily build a Fortran-based extension. It has an extensive software process, CI and documentation. There's around 194 tests running on 3 platforms, in fact 4, because we also run tests on 32-bit Linux, from Python to 7, including Python to 7, and then from Python 3.4 to 3.7. Documentation on read the docs, contributing document, release note, MIT license, mailing list, package available on Conda, and coverage is like 90%. What's next? SciPy sprint will be on Saturday. We're going to finalize the Conda package associated with the latest release. We're going to improve the documentation, add more example projects, provide guidance to integrate Scikit-build in existing project. But long term, we can also reach out to NumPy and SciPy folks. There's clearly some more work that could be done. We're going to help with a proposal for packaging native libraries into Python wheels. Right now, when you create wheels, if your module statically link against your dependency, everything go well. But now if you have shared libraries, there's not yet an easy way to package them. We're going to work on implementing the PEP 517 to have a build backend where we decouple from setuptools and leverage the new dislib libraries. Thank you. Thank you all the contributors. Some of them are in the room or at the conference who help work on that project. Thank you to all the issue reporter. And also thank you to the PyPA, the Python Packaging Authority, the PEP contributor, and also the wider community. Scikit-build, the link for that talk are on bit.ly, scikit-build-talk, and the source code is available on GitHub. Voila, if you have any question.
There's another microphone over here, and I'll run around the room if I see your hand up. And I was wondering if we could get our first questions from someone who is either first-time attendant of SciPy, maybe a student, a lady, someone who didn't understand anything about this talk, who's completely new to all of this, and wants a pointer where to start? I want to see a hand. We have, I think, 10 minutes. I found a hand. Very good. Okay.
Okay, thank you very much. This is actually my first time here. Based on what you said, it's something that will be very helpful to me in what I do. So I build a lot of software on computers for faculties at my institution. So you talk about Scikit-build and being different from CMake, but towards the end, it sounded a lot like they are very similar, because you still have to set some of the environment parameters to be able to build your software. You have that option built in, which is exactly what CMake does. So can you explain that a little bit more?
Yeah. Basically, if you have you give a CMake list to someone working in the Python community, they don't know what to do with it. The interface is pip will or setup.py bdist_will. And there's a lot of work you need to do between you have a CMake list that builds some libraries, and then you can package them in the wheel and deliver them. And Scikit-build is here to bridge setuptools with CMake and make sure everything is packaged in a meaningful way and available to the user. Does that answer your question?
Go ahead. Another question there.
My question is, are there any libraries that are using this yet?
Yes, we use that, for example, to create the ITK wheel. ITK is a pretty exhaustive C++ template-based C++ library that Matt's going to describe in more details this afternoon. And now ITK, for example, is integrated with the Jupyter notebook, and that's made possible by generating ITK wheel, and we use Scikit-build for that.
Have you seen any issues with Scikit-build interacting with build isolation in pip10?
We tried it for the tutorial, and we didn't have any particular problem.
Moving to you over here, another question. Thank you.
Hi. I'm not super familiar with binary extensions, so excuse me if this is a trivial question. But I was wondering why it is, you mentioned that IDEs are not typically supported in building binary extensions. I was wondering why it is that that is so, and what Scikit-build has done to change that, if anything.
Yeah, for example, right now, when you want to build your extension, you import extension from distutils or setuptools, and then you list the .c file. But to go from the .c file to managing them in a meaningful way in your IDE need to be aware of the compile flag, you need to be able to do rebuild in your IDE. You are missing something here. You can still open them in Emacs or VI and sort of like craft your script to build it in the same way, but it's very error prone. With CMake, you can choose, you have a concept of generator. It means you say generate a build system for a given version of Visual Studio, and then you will have, for example, a solution file, and then you can open that, and you can rebuild your extension like that. You can also debug it more easily.
Wonderful, thanks.
Thank you for your question. Over here.
So if I have an existing project using setuptools, for example, that builds already, if I switch to Scikit-build, would I get any cool new functionality from that switch? Or is it mostly just they do the same thing and it's just alternate ways of doing the same thing?
Are you asking for regular, for pure package?
No. I mean, like I have a Python project that has like Cython extensions and C extensions, and we use setuptools to build that right now. But if I wanted to use Scikit-build, would I get any cool new features if I wanted to use that? Or do they mostly just do the same thing and I wouldn't really get anything out of it?
No, if it works well for you right now, there's no need to transition to Scikit-build. It's now if you start to have like some Cython extensions, some compile code, some Fortran code, and you want to more easily manage that full set, that will be useful.
So it's more, if I'm starting a new project that has a bunch of compiled extensions, then I should look in Scikit-build instead of setuptools for managing all that stuff.
Yeah. Yeah, and basically you will write one or multiple CMake lists. You can have multiple. They include, you can recursively include them, and then you will describe in each folder how you build your your code. And also, it's also useful if you have, for example, a library that is not only used in Python, but provide like a backend that can be used in Julia or in other language. It means you build your backend with CMake, and then you want to link against that backend. And when you link against libraries, you want to inherit of all the build flag, the requirements. If you use C++11, C++17, you want to make sure that the requirements for building your project are transitively propagated, and with CMake, you can benefit from that. It's more useful for like larger projects.
I know you mentioned a little bit about it doesn't replace Conda as a package manager. I was wondering if you could comment on how it may compare to, say, CondaBuild, which also allows you to build Python packages, or not just Python, other packages with C extensions and other stuff.
Yeah, basically in Conda, you have your recipe, and you call whatever you need to call to build. It means between the source code and what you do in your recipe, there's room for improvement. And for example, what we do to create the ITK Conda package, in our recipe, we just extract the content of the wheel and depackage it in a Conda package. But you could also directly build the wheel on Conda using the compiler available on Conda, and then repackage that in your package.
I see. Thanks.
Time for one last question. Any burning question? Short one, though. Okay, coming to you with the red over there. Red vest. All right.
Thanks. So I have never written a CMake file, and is there like a template that Scikit-build can provide if I just have a simple, Cython package?
Yes, we have like a few Hello world, Hello-pure, Hello-cpp, Hello-Cython, and there are very small examples that you can build on. And we are working on cookie cutter template that include the full integration with AppVeyor, Travis, and Circle CI to build the wheel on all the platform in a very easy way. And also upload to PyPy, and also upload as a GitHub release. It means every day you do your nightly build, your daily build. We automatically, we have another project named GitHub Release. It's a Python package that allows us to have a latest tag on GitHub, and we follow the head of your repo, the master branch. And it's like a bleeding edge release. And then when you want to set up the CI for your other project, you're going to specify the HTML page corresponding to that GitHub release. It means you can build all your dependency using the bleeding edge by automatically downloading the wheel from the GitHub release. It means there's more to it than just Scikit-build, but to provide like a meaningful ecosystem. Thanks, everyone. And if you have questions, come talk to me. Again, we're going to be at the sprint on Saturday.
Thank you. Thanks. Let's thank the speaker.